The salmon climb by tens. 10, 20, 30, then 40. Same jump means a line.
Welcome to the salmon run. Take a look at these two rivers. They both climb the exact same elevation distance, and the salmon migrating upstream have to navigate them both. But the paths these two rivers take behave in completely different ways. Looking at this diagram floating over the first river, we can see exactly how it climbs. The elevation increases by adding the exact same amount in equal steps, like a steady, predictable staircase. We call this linear change. Now watch as the overlay expands to map the second river. Instead of adding a flat amount, this path scales upward by multiplying by the exact same factor in every step. This creates a steep, sweeping ramp. We call this exponential change. Right here at the bottom of the mountain, the paths might look close together, but as we follow the math further upstream, the addition on the left and the multiplication on the right will drive these rivers miles apart. Choosing the correct model lets us predict exactly where the salmon will end up. Let's see how these two types of growth look in the wild. Imagine a forest where squirrels are stashing acorns into two different savings accounts for the winter. This panel tracks account A. Every single month, the squirrels gain a flat $50. Because we are adding the same amount over equal intervals, this is an additive, linear rate of change. But look at account B alongside it. This account grows by 5% each month. Earning 5% means we multiply the current balance by 1.05. Because we are applying a multiplier rather than a flat addition, this growth is exponential. Early on, 5% might look like a small addition, but if we confuse a percentage multiplier with a flat linear rate, our model will completely miss how quickly that stash of acorns snowballs over the long winter. Over in the marsh, a heron is tracking fish populations using data tables. Take a look at this table hovering near the water. It shows a sequence of outputs, 10, 20, 30, 40. But the important part is the highlighted gap between each row. Notice how each jump is exactly the same. We add 10 to get to the next step. Because the gap is an equal difference of 10, we know for certain this data comes from a linear model. Let's test this out. Look at the second table that just appeared. The outputs are 10, 20, 40, 80. Take a moment to think. Does this population grow by an added amount or a multiplied factor? If you look closely at the gaps, you'll see they don't share an equal difference. Instead, the intervals jump by a consistent multiplier of 2. Since the factor is constant, this data is exponential. Raw numbers in a sequence can trick the eye. Checking the relationship between consecutive outputs, finding out whether they share a difference or a factor, is the only reliable way to identify how the data behaves. Sometimes we don't have a table, we just have a description of the environment. Imagine a pond where the population of frogs on lily pads doubles every 6 hours. We can translate that single English word directly into math. Watch this overlay map the population. Doubles is just an instruction to multiply by 2. 1 becomes 2, 2 becomes 4, 4 becomes 8. Because this scenario relies entirely on repeated multiplicative change, it must be modeled exponentially. A linear model based on addition simply wouldn't work here. Words matter. When you hear vocabulary like doubles, triples, or percent change, you can treat those words as direct signposts pointing straight toward an exponential model. Whether we are looking at rivers, forests, or marshes, the math governing how things grow always comes back to the same core ideas. Let's bring this all together on a single cheat sheet.
So, the rule for recognizing linear change is simple. It relies on equal differences over equal intervals. The rule for recognizing exponential change is just as straightforward. It relies on equal factors over equal intervals. Once you master these two rules, you can read the pattern of any dataset, translate situational words into math, and choose the right function model. That model gives you the power to reliably predict the long-term future of any scenario you encounter. So the next time you face a new pattern of growth, just ask yourself, is the change a constant difference or a constant factor?
Adding the same is linear. Multiplying is exponential and faster. Exponential always wins later.